Exercise 6.25. Prove that for every n greater than or equal to 2, the line is not homeomorphic to Rn. Now, the reason for this is basically that to disconnect a line into a couple pieces, all you need to do is take away one point. But if you take away one point from Rn with n greater than or equal to 2, the set you get is still connected. Okay, so they can't sort of be the same space. All right, so let's try to prove that. Assume for contradiction that they are homeomorphic, so there does exist a homeomorphism from the line R to Rn for some n greater than or equal to 2. Then, since the point 0 is a cut set of the real numbers, and its complement has a separation, the positive real numbers and the negative real numbers, then we have a theorem that tells us that the image of that cut set under this continuous function f is going to be a cut set of the target Rn. Okay? Meaning that the complement of this one-point set is disconnected. But that's a contradiction. We can show that that complement of the one-point set is in fact connected. So the way we do it is to obtain this sort of punctured n-dimensional space as the image of a connected set R plus cross Sn minus 1 under a continuous function, okay, which we know means that the image has to be continuous. The way we build this function is sort of like polar coordinates. We're going to take a positive real number R and a point Y on this unit circle in Rn, and well, we'll take all those points on, unit sphere in Rn. We'll take all those points on the unit sphere, and we're going to multiply them by the positive real number, which takes that unit sphere and just expands it to a sphere of radius r, centered at the origin in Rn. And then when we add f of 0 to that, that just shifts the sphere so that the new center is f of 0. Okay. So if you think about all of the spheres you get for all the different possible r values, that those spheres fill up the entire n-dimensional space except for that point at the center of all of them, f of 0. Okay. So the union of all those spheres, the image of this function g is Rn minus f of 0. And that does it. Now, you should ask, where does this proof break down in the case when n equals 1? Because these certainly are homeomorphic when n equals 1. And just as in a previous problem, it has to do with the unit sphere in R1, right? So that would be S0, set of all points at distance 1 from the origin in R, and that's just a 2-point set, right? Negative 1 and 1. And in that case, that is a disconnected set. So this would break down right here. All right.